Okay, great. So today we're going to talk about randomized algorithms. And here I don't mean that the input is random, but actually the algorithm itself is making random decisions. So we're still interested in worst case analysis of algorithms, but where the algorithm is randomized. And there are two kinds of randomized algorithms that we're going to talk about. One is Las Vegas. In a Las Vegas randomized algorithm, the algorithm is always correct, but its running time is a random variable. Okay. And what we'd like to show, for example, is that this runtime, this random variable, is small in expectation or, say, with some high probability. And then the other kind of randomized algorithm we're going to talk about today is Monte Carlo randomized algorithms. It's kind of the opposite. These are algorithms that are always fast. We have a deterministic bound on their runtime. Like the algorithm always runs in n squared time, at most n squared time. But its correctness is a random variable. Okay? So what do I mean by that? So always runs quickly, runs within some fixed time bound, but correctness is random. So what I mean by that is, like, for example, for all inputs x, the probability over the random decisions made by the algorithm. So the algorithm, you can think really, what is a randomized algorithm? It's really a deterministic algorithm that has two inputs. One input is the traditional input x, like the array that needs to be sorted for quicksort. The other input is like a big random string. That's basically, the source of randomness for the algorithm. So whenever it needs to make a random decision, it looks at the next bit or the next few bits in that random string, and based on what those random bits are, it makes its decision. Okay, so the probability over those random strings, over that random string, the probability that a given input x with random string r is correct. This we want to have some control of. This maybe is at least 9 over 10 or something like that, right? So in a Monte Carlo algorithm, it always runs in some time, like n squared or n log n or whatever, but the correctness is not always guaranteed. Okay, for all inputs, for a worst case input, you do have a bound on what the probability of being wrong is. So here, the probability of being wrong is at most a tenth, right? Based on the random inputs, the random string fed into the algorithm, but it's not 100. It's not 0. The probability of being wrong is not 0. Okay. Whereas a Las Vegas algorithm would be like, it's always correct. And what we know is that, say, for all x, the expectation, again, over r, of the runtime of a given inputs x and r, this might be, let's say, O of n log n or something like this. Right? So here we have an algorithm A that's always correct. No matter what r is, no matter what x is, you will get the right answer when you run A on xr, but its runtime is a random variable. Okay? So an example of this would be like quicksort. Right? Quicksort, we talked about that earlier in class when we talked about sorting and merge sort. If you're unlucky and pick a bad pivot, then your runtime might be slow. But no matter what happens, you are guaranteed to actually sort the array. So for all x, for all arrays x that need to be sorted, you will sort it. Monte Carlo, for example, something that you've seen even outside of this class would be like polling, right? So you have a population of voters, and you want to know what fraction of those voters are voting for candidate A. And I'm happy to get an answer that's within 1% of the true answer. There's some error in polling, but I want to be fast. Meaning I want to talk to as few people as possible and poll as few people as possible. So one way to do that is just sample random people and ask them, who are you voting for? And then based on those statistics, I'll extrapolate to figure out what fraction of the total population is voting for candidate A. Now, I might get very unlucky, right? maybe my population has 1 million people, and I only polled 100 people, okay? And maybe I'm unlucky, and everyone I polled, all the 100 people I polled, just randomly happen to be voting for candidate B, even though in actuality, an overwhelming majority of the million population is voting for candidate A, right? So I was unlucky in my random choice of who to pick to poll. And I got an estimate of the number of votes for the candidates that's wrong because of the unluckiness in my randomness in who I chose to pick here. So that was the unluckiness in my R, right? So there, I'm always fast because I know I'm only going to poll 100 people, so I'm only going to take 100 time steps. But the probability that I give you an estimate of the votes that's, say, correct to within 1% error is not 100%. Right? There is some probability that my poll is not representative of the actual population, of my sample is not representative of the population. So that would be like a Monte Carlo kind of approach. And we're going to talk today about several algorithms. So we're going to talk about a Las Vegas algorithm, namely quicksort, and we're going to analyze it rigorously. And then we're going to discuss some Monte Carlo algorithms as well. So before I do this, since we're going to be dealing with a lot of random variables, I do want to just put up a couple reminders about things you've learned in classes like CS70 that I will expect you to remember for the rest of this lecture. So probability recap. Right, so we're going to be talking about random variables here, and the random variables we consider will always have real values, actually usually integer values. And if they have integer values, then remember just expectation. The expectation of x is just defined to be the sum over all k from minus infinity to infinity of k times the probability that x equals k. And there's a property of expectation, which is linearity of expectation, which we're going to use a lot, which says that if you have two random variables, x and y, and you have scalars a and b, the expectation of ax plus by is a times the expectation of x plus b times the expectation of y, regardless of whether or not x and y are independent. They don't need to be independent for this to be true. And the last thing that I wanted to remind you of is Markov's inequality. Which says that if x is a non-negative random variable, then the probability that x is too big, we can bound the probability that x becomes big in terms of its expectation. For all t bigger than 0, the probability that x is bigger than t is at most the expectation of x over t. Okay? So, or you might have seen it written as the probability that x is bigger than t times its expectation is less than 1 over t. So you can't be, it's unlikely that you're that much bigger than your expectation if you're a non-negative random variable. Okay? So I will not prove these things. You can go look in 70 or other resources if you don't remember proofs of these. I'll just use them as true. Okay? So good. So I'm going to cover today one Las Vegas algorithm, which is quicksort. And then I'll cover several Monte Carlo algorithms. So we already know what quicksort is. I'll give you a little recap. The main thing is, how do you analyze it? So quicksort. So remember, what is quicksort? Again, you're given an array A that has n entries in it, and you'd like to sort the array. Okay? It's a length n array. What does quicksort do? Quicksort says, pick a random element in this array, and then compare this random element with all the other elements of the array. Everyone that's smaller, you move to the left. So let's call this element x. Everything that's smaller than x goes here. Everything that's bigger than x goes here. You don't necessarily sort these arrays. You just scan and then put them in here. You don't put them in here necessarily in sorted order. And then you recursively sort the left and the right. By calling quicksort again. Okay. Now notice I put strictly less than and strictly greater than. I will assume in this lecture that all the inputs of the array A are distinct. There are no two elements that have equal value. And remember, I did the same thing when we covered merge sort toward the beginning of the semester. And that, as I mentioned then, is without loss of generality. And if you don't remember why, let me remind you, without loss of generality, for all I not equal to j, ai is not equal to aj. I can assume that all the array elements are distinct. Why? I can create a new array B where bi is actually the pair ai comma I. And then I'll sort B lexicographically. Right? Meaning, if I want to compare two elements of B, I first compare the first entry in the pair. And if they're different, okay, then whoever's smaller is smaller. But if they're equal, then I break ties by comparing the second element in the pair. And the second elements are always different, because the second elements are 1, 2, 3 up to n. So right, the elements of B are distinct. So B has a unique sorted order. So indeed, nothing will be equal to the pivot. Things will either be strictly less than or strictly greater than the pivot. Okay. So good. Of course, what I'd like the pivot, and I said this earlier in the semester when we were talking about sorting, I would like the pivot, ideally, to be like the median of the array, the thing that's halfway in sorted order, because then I get a nice recursive subproblem with n over 2 on the left and n over 2 on the right. And if you write the recurrence relation, t of n is 2 times t n over 2 plus O of n. The O of n is because it takes linear time to do the pivot. That would solve to n log n, and I would be happy. The problem is, I might unluckily choose a pivot that's not near the median at all. I might unluckily choose a pivot that, for example, is the smallest element in the array. And what would happen then? Then nothing would be less than x, and n minus 1 things would be bigger than x. And then I would have a recurrence relation that looked like t of n is equal to t of n minus 1 plus O of n, which implies that t of n is O of n squared, which is not great. So the running time of this, I mean, that's if I'm unlucky every single time, and I always pick a pivot that's, let's say, the smallest element in the array. So in the worst case, the runtime might be n squared. In the ideal case, where I keep picking good pivots, my runtime would be n log n. What can I say about the expected runtime of quicksort over the random decisions it makes? So expected runtime. Okay. So there are really two key insights that once you realize make the analysis a whole lot simpler. The first insight, is that the runtime is proportional to the total number of comparisons. Right? Why is that? Well, let's try to unpack really what is the runtime of quicksort. Well, you have this array of length n. You pick a pivot. I'm assuming that picking a random pivot takes constant time. You pick that random pivot, and then for each other element in the array, you do a comparison. You compare that pivot with that element in the array, right? So the runtime here, at this level of recursion, was n, which really was also the number of comparisons to the pivot. And then you recurse on these arrays. This array here will have its own pivot. This array will have its own pivot. And then here the runtime is going to be proportional to the length of this subarray. But again, the length of this subarray is the same as the number of comparisons at this level to the pivot, because everyone else is going to compare themselves to this pivot. So kind of every unit of runtime that's happening in this algorithm is related to comparing some element in some array at some recursive sublevel with a pivot. Okay? So at the end of the day, the runtime is proportional to comparisons, right? The thing that's actually taking you time is doing these comparisons with pivots, but doing comparisons. So the runtime is proportional to comparisons. And the second insight is you never compare AI with AJ more than once. Right? Once you compare two elements, you will never compare them again. Why? Well, if you're comparing two elements, when do you do comparisons in this algorithm? It's when you're partitioning around the pivot, right? So if you're comparing AI with AJ, the reason you're doing that is because one of them is the pivot. So let's say AI is the pivot. Doesn't matter which one. Okay? So AI is the pivot. You did a comparison with AJ. Now AJ will either be on the left side or the right side. And then you're going to do some recursive call on the left and the right. AI doesn't appear in those recursive calls, right? Over here, you partition in the left and the right. X knows where it goes. X goes right here. And then you only have to recursively sort this and this. So all these people who just got compared with X will never get compared with X ever again, because X doesn't live in their recursive subtree. Okay? So you'll never compare two elements more than once. You'll either compare two elements 0 times. There are some pairs that you never compare. For example, you never compare this element with this element, right? Because they got split at this recursive level, and they never have a chance to get compared with each other again. So you'll either compare elements with each other 0 times or 1 time, but never 2 or more times. Okay? So good. So now we can write the following. We can define indicator random variables. So the analysis now. Define indicator random variables, xij. Xij is 1 if the ith smallest element is ever compared with the jth smallest and 0 otherwise. Right? And we know that runtime is proportional to the number of comparisons. What is the number of comparisons? It's the sum over all ij, xij. Right? So that means, 1 plus 2 imply that the runtime is proportional to, so it's almost some constant times the sum over all I less than j of xij. Which means that the expected runtime by linear is well, it's at most the expectation of the right-hand side. And now I can use linearity of expectation. If you sum up a bunch of random variables that could be dependent with coefficients, you can push the expectation inside the sum. So this is exactly C times the sum I less than j of the expectation of xij. What is the expectation of xij? It's 0 times the probability that xij is 0, plus 1 times the probability that xij is 1. So this is exactly the same as C times the sum over all I less than j of the probability that the ith smallest and the jth smallest elements are ever compared. Basically, it's the probability that xij is 1. Right? This is just the same as saying the probability that xij is 1. So if we can understand that, if we can compute that quantity, we can plug it into the summation and then get our answer. And that's exactly what we're going to do. Okay. So let's do that. So we want to understand the probability that the ith smallest is ever compared to the jth smallest. What is that quantity? Well, let's think about it. There's the initial array, which has length n. And even though it doesn't come sorted, let me just, for the sake of the picture, let's just pretend that it came sorted. So like here's the ith smallest here, and here's the jth smallest here. Okay. Now we are going to pick some random pivot, and then we're going to recurse into a left and a right subproblem. Now, if the pivot is here, or if the pivot is here, what does that mean? Remember, I'm pretending that this is in sorted order. Really, you should imagine, what I really mean is if the pivot is something that's smaller than the ith smallest, or if the pivot is something that's larger than the jth smallest, then what does that mean? It means that I and j will still stay in the same recursive subproblem, right? So for example, if the pivot is here in this left blue region, then I'm going to run into a situation where one of the recursive subcalls will still have I in it and j in it. And then, the things, let's say if the pivot's here, the things to the left of it will be a different call. And there'll be more here. Or if it's in this region, I'll still have j and I also in the same recursive subproblem, and then some pivot, and then some stuff over here. Right? This is if pivot is in the blue region. On the other hand, if the pivot is not in the blue region, so if the pivot is in this red region, then I know for sure that I and j will not be in the same recursive subproblem from the next recursion onward, right? Because either I or j will be the pivot, in which case they're done. They no longer appear in any recursive subproblems. Or the pivot is something in between them, in which case I and j will get split. Okay? So if the pivot is in the red region, then this level of recursion is the last chance for I and j to be compared. Okay. And we know that for any I and j, they will eventually be split. Right? How do we know that? Because the leaves of the recursion, the base case is when we just have an array of length 1. Right? So I and j were originally in the same array. There's a bunch of recursions. Eventually, I will be in its own base case by itself. J will be in its own base case by itself. So eventually, they did get split. Right? So there might have been a bunch of, if we just trace the recursion tree is a perfect binary tree, right? This is everything. Then there's a left subtree and a right subtree. Then there's a left and a right here, and a left and a right here. Some of these might finish early because sometimes, we might end up with a case where one array has size 1 before the others do at the same recursive level. But every internal node has exactly 2 children. And what I'm saying is there's going to be some, if you just follow from the root downward, there is some point, there is some kind of path where I and j are together that entire path. So I and j here both got into the left subtree, they both got into the right subtree, and then they got split right here. Maybe I went here and j went here, or maybe one of them was the pivot. But the point is, there's always going to be some kind of prefix of recursive calls where they're together, and then eventually they get split. Okay? So that prefix, I should have drawn it in blue. And that prefix, when there's always together, corresponds to always picking pivots that are in the blue region. Right? But eventually, we will pick a pivot in the red region. That has to happen just because, as I mentioned, eventually the leaves of the recursion, we know they're separate. So that red region had to happen at some point. So good. So let's focus our attention on that, the first time when we hit the red region. Okay? This is the last chance that I and j have to be compared. Now, what's the probability that they are compared? Well, they're compared, I and j compared, if and only if either I or j is the pivot. Right? If I is the pivot, then you will compare it with j. If j is the pivot, you will compare it with I. But if the pivot is anything in between, then they'll be split and they'll never have a chance to be compared with each other. So this implies, so what, given that we're choosing something in this red region, the person we actually choose in the red region is uniformly at random. Right? So that implies that the expectation of xij, or in other words, this probability, is equal to, well, there are two ways to pick a pivot from I and j, either I or j, and the total number of people here in this red region is exactly j minus I plus 1. So that's it. The expectation of xij is exactly 2 over j minus I plus 1. So let's try to plug that in over there. So this implies that the expected runtime is big O of the sum I less than j of 2 over j minus I plus 1. So let's try to understand this a little bit better. Right? So we're saying here the sum I goes from 1 to n minus 1. The sum j goes from I plus 1 to n of 2 over j minus I plus 1. Let me pull the 2 out. Okay. So what is this quantity? Well, let's try to rewrite it in a way that's easier to digest. When I is equal to 1, right, let's start at the end. Let's start in the case when j is actually equal to, let's start when j is equal to 2. So we have 2 minus 1 plus 1, which is 2, I guess. And then when j is 3, because j has to go from I plus 1 to n. When j is 3, we have 3 minus 1 plus 1, which is 1 third here. So we have basically a half plus a third plus a quarter plus plus all the way up to n minus 1 plus 1. So 1 over n minus 1 plus 1 over n. Right? This corresponds to j being 2, j being 3, j being 4, etc. When I is equal to 2, that contributes to the sum, again, 1 half plus 1 third plus 1 fourth plus plus 1 over n minus 1. Right? Because in the last case, when j is n, we have n minus 2 plus 1. So that's 1 over n minus 1. And let me just do one more. I equals 3. We have, again, a half. When j is 4, we get a half. When j is 5, we get a third plus a quarter plus plus 1 over n minus 2. So the observation is now, let's just look at this kind of like column-wise now. This, by the way, goes all the way down to the last possibility for I is when I is equal to n minus 1. So this half appears in all of them. So this is going to give us n minus 1 times a half. This third appears in all but the last one. Right? When I is equal to n minus 1, j can only be n. That's going to contribute a half. There's nothing that contributes a third. So this is going to contribute something like n minus 2 plus n minus 2 times a third, plus, again, n minus 3 times a quarter, plus dot, 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 plus 1 times 1 over n. This is just kind of looking at it column by column. How many quarters are there? There's n minus 3. How many thirds are there? There's n minus 2. How many halves are there? There's n minus 1, etc. And let me be a little bit sloppy. Actually, it turns out that this is not super sloppy. You'd still get roughly the same answer up to a constant factor. All these things here, I'm just going to bound by n. This thing here is certainly at most n. n minus 2 is also at most n. n minus 3 is also certainly at most n. And even this 1 is certainly at most n. So at the end of the day, this double sum, remember there was a 2 out here too. So this double sum is at most, it's at most 2, and then all these n's, I'm just pulling out a factor of n, 2n times a half plus a third plus a quarter plus dot, 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 plus 1 over n. Right? Which is exactly, you probably have seen this in some class, maybe in 70, the harmonic series, which is proportional to log n. So this would basically, this tells you 2n log n, which is what we wanted. If you don't remember why the harmonic series is proportional to log n, let me at least show you the upper bound. The lower bound is proven using basically a similar kind of argument. So let me plot the following. So let's see, this is 1, this is 2, this is 3, this is 4, 5, etc. Consider the following sequence of rectangles. Right? What is the area of the total area of this black shaded region? It's exactly that sum. It's a half plus a third plus a quarter, and let's make it go all the way up to out here. There's an n here. Okay. On the other hand, let's draw another curve. And this curve, this blue curve here, is just f of x is equal to 1 over x. Right? So what should be clear is that the area under the blue curve is bigger, in fact, strictly bigger than the black area, the area in the rectangles. Right? So that tells us that this sum, 1/2 plus 1/3 plus dot, 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 plus 1 over n, this sum is at most the integral from 1 to n of 1 over x dx, which is exactly ln n. Okay? So that just tells us that this here is at most 2n ln n. So good. We proved exactly what we wanted to prove, that the runtime is big O of 2n ln n. So it's big O of n log n. So that's it for quicksort. So that's just the expected runtime, but you could ask the question, well, okay, so maybe in expectation it's 2n log n, but is it usually 2n log n, or is it highly varying? Is the variance very high in that runtime? Like maybe there's a pretty, even though on average the runtime is n log n time, maybe there's a pretty decent chance that it actually takes n squared time. There are tight analyses you can give that show that's not the case. In fact, with really high probability, the runtime is very close to n log n, some constant times n log n. I will not show that today, but what I can say is, one thing you could do is just immediately use Markov, right? So I reminded you what Markov's inequality is. Right, so Markov says it gives you a bound on the probability that a non-negative random variable becomes large. So let's just define a non-negative random variable. Let t equal the runtime of quicksort on A, on this input A. This is a random variable because it depends on which pivots you pick randomly. Markov says, and what do we know? We know that the expectation of t is at most some constant, Cn ln n. So the probability that t is bigger than 100 C ln n is at most 1 over 100 by Markov's inequality. So with 99% probability, I know that my runtime is bounded by some fixed constant, namely 100 C times n log n. Okay, so that's a little, that's not super tight. You can actually get, you can get much better kinds of bounds than this using more sophisticated things than Markov's inequality. But I just wanted to show you an example of using Markov. Okay, so Markov gives you this very easily. Okay, so that's all I wanted to say about the runtime of quicksort. And notice you could try to do the same kind of analysis for quick select as well to show that quick select, like if you want to do median, you could do a similar thing where you pick a random pivot, you compare everyone with a pivot, and depending on how many people are to the left or to the right, you'll either only recurse on the left or only recurse on the right. You don't need to recurse on both if you're just doing median or select. And you can show that in expectation your runtime would be O of n instead of n log n. The reason being that basically in that version where you don't recurse on both sides, you only recurse on either the left or the right, this expectation changes. It's no longer, the probability that you compare I with j is no longer this quantity, it's something else. And then if you figure out what that is and you sum that up, you'll actually get a summation which computes out to linear instead of n log n. But I won't do that today for you. Okay, so that's a Las Vegas algorithm. And now I wanted to show you some Monte Carlo algorithms. Okay, so Monte Carlo. And the first problem I'll talk about is verifying matrix-matrix multiplication. Okay, and we're going to cover an algorithm here. It's a Monte Carlo randomized algorithm called Frey-Wald's algorithm. Okay. So what's the problem? You're given A, B, and C, which are n by n matrices. And the question, does A times B equal C? That's the question. Okay. Now, what's the motivation here? The motivation you can think is, okay, so yes, I could compute A times B myself. Naively, with for loops, that would take n cubed time. I could use Strawson to do a little bit better, or I could use the more sophisticated algorithms that get even better. But I don't know an n squared time algorithm for matrix multiplication. At least humanity does not know one yet. So suppose that there's some big company that has 1 million machines on the cloud, and they provide a matrix multiplication service. Okay, this is, of course, kind of a made-up toy example, but companies that have, there are, in reality, companies that have millions of machines on the cloud, and you can submit jobs, and they'll do them for you and charge you money, right? So this is a real kind of problem, even though maybe matrix-matrix multiplication is not exactly what people usually use them for. But so the point is, there's some company that has all these machines in the cloud. What I'd like to do is I would like to just upload a file describing my two matrices, A and B. I'll send A and B to the cloud, to that company. And then the company will do its computation. It has a million machines. It can do those n-cubed for loop computations in parallel really fast. And then it'll just send me back C. Okay? So yay, I know C. However, what if the company gave me the wrong C? And what do I mean by that? So A, the company might just be malicious and might be intentionally giving me the wrong C. But probably more realistic, the people who implemented that package at that company that does the computation for me, they're human. They might have bugs in their code. And for whatever reason, the A and B I gave them triggered some bug conditions in their code, and the C they gave me is not right. Okay? And it might be not right in subtle ways. Maybe like all entries except for one are right, but that one entry, because of some special case in their code, that one entry is wrong. What I want to know is, can I catch that? Okay? Can I? And of course the answer is yes. I can catch it because I can always multiply A times B myself, and then just check, is what I got actually equal to C or not? But that defeats the purpose. Right? That defeats the whole motivation of why I went to the cloud in the first place. I don't want to compute A times B myself because that takes a lot of time. That's the whole reason I paid the cloud to do it for me. Right? I'm happy to let them take n-cube time because they have a million machines. I personally am only willing to spend n-squared time. Okay? So is there a way to do it? Is there a way to, in, let's say, n-squared time, figure out, have a good confidence that A times B is actually equal to the C that the cloud gave me? And it turns out that the answer is yes. And the reason it's yes is there is an algorithm called Freival's algorithm. So what is the algorithm? Pick x1, x2, up to like xt, each in 0, 1 to the n, independently and uniformly at random. That's the first step. The second step is a for loop for I equals 1 to t. If ABXI is not equal to CXI, return false. Otherwise, at the end of the for loop, I'll return true. Okay. So what should be clear is, if C actually is A times B, this will definitely return true. Because if C actually is A times B, all of these xi's, ABXI, will equal CXI. So I'll go through this for loop, I'll never find a problem, and I'll return true. How about if A times B does not equal C? Well, even if A times B does not equal C, it might happen that ABX equals CX. Why? For example, what if x is 0? Anything times 0 is equal to any other thing times 0, right? But 0 is not the only case. There might be other, there will be other x's that fail to spot that there's a problem. And in terms of runtime, notice that because multiplication is associative, to compute ABXI, I never actually need to compute A times B. I can first compute B times xi, and then I can compute, that's a vector. B times xi is a vector. And then I can compute A times that vector. So I just need to do 3 matrix vector multiplications per for loop iteration C times x, that's one matrix vector multiplication, B times x, and then A times that, so 3. So the total runtime is O of, there are t iterations through the for loop. Each iteration I have to do 3 matrix vector multiplications. How long does it take to multiply an n by n matrix times an n-dimensional vector? N squared time, just using a for loop. Just using 2 nested for loops. So t times n squared. What is t? I'll tell you in a second. So we already said if a times b equals c, this will definitely say true. What if a times b does not equal c? Is this going to say false? Or is it going to say false at least with high probability? So let's try to understand that. So claim 1, if a times b is not equal to c, then the probability over a random x chosen this is a uniformly random x chosen this way. So so uniformly at random. So each bit, each entry in x is uniformly at random either 0 or 1. So if AB is not equal to C, then I claim and we'll show that the probability over x that ABX is equal to CX is actually at most a half. We're going to prove that, but if we have that, then claim 2, let's use that, claim 1, the probability that the algorithm Freyvold gives the wrong answer is at most 1 over 2 to the t, which we can say is at most p if we pick t to be, let's say, the ceiling of log base 2 of 1 over p. So that's what I'm going to choose t to be. So this is basically going to be O of n squared log 1 over p, where p, you can think p is like a user-specified parameter. What do I want my confidence level to be? I want to be confident about the answer with probability 1 minus p. Okay? So, p is a parameter that I can choose. And the runtime is going to depend on how much confidence I want to have. And the proof of claim 2, why is this true? Why is it at most 1 over 2 to t? The proof is just the for loop iterations are independent, and I only can give the wrong answer if AB is not equal to C, and for all I, ABXI is equal to CXI. Right? Then I'll be fooled into thinking that they're equal when they're not. But by claim 1 implies that the probability that for all I, ABXI is equal to CXI is equal to the product over I of the probability that ABXI is equal to CXI. This is using independence. Independence of the xi's. And this is at most 1/2 for each one, and there's a product, so 1/2. This I goes from 1 to t, 1/2 to the t, as desired. Okay. So that's that. And now, what about the proof of claim 1? So just define a new matrix D to be AB minus C. And D, notice D is not 0 since AB is not equal to C. Since D is not equal to 0, there must be some particular entry of D that's not equal to 0. Right? So D is this big matrix, n by n. I know it's not 0, so all I'm saying is there must be some entry which is not 0. So this is the ith row in the jth column. There might be many such entries which are not 0, but there's certainly at least one. And then now notice that, now let's look at this j here. Notice that d of so what do I want to say? If d of x, if dx is equal to 0, then d times, I'll call it x flip, this is my weird notation for x, flip j is not equal to 0. Okay. So what do I mean by x flip j? I mean, there's some vector x here, which is an n-dimensional vector. This is the jth entry. So there's some stuff here which I don't really care about. But in the jth entry, maybe x is a 0, and when I flip, that means that when I do flip j, I change it to a 1. Or if it was a 1, I'll change it to a 0. So this is x, changing to x flip j. So I'll change the jth entry from a 0 to a 1 or a 1 to a 0. So I claim if dx equals 0, then dx flip j must not be 0. Why is that? Well, let's say that the j, okay, so why? Okay, so case 1 is that xj is 0. And let's label these columns. This column, the first column is d1, the second column is d2, the third column is d3, etc. If xj is 0, that implies that that d of x flip j is the same thing as d of x plus the jth standard basis vector, which is exactly dx plus dej. This we said was 0, right? We're claiming that that's 0. What is d times ej? It's just the jth column of d. So this is dj. But we just said that dj is not 0 because its ith entry is not 0. So this is not equal to 0, since in particular dij is not equal to 0. And case 2 is similar. If xj equals 1, that implies that dx flip j is equal to d of x minus ej, which is dx minus dej, which is exactly minus dj, which again is not equal to 0. Right? So what this says is, so you can imagine now what this observation is telling us is, look, how many x's are there in the world? There are 2 to the n of them, right? X could be anything, any binary vector of dimension n. So there are exactly 2 to the n possibilities for x. So look at the 2 possibilities, 2 to the n possibilities for x. Pair each x with its flip. So basically now you have 2 to the n minus 1 pairs. Right? So let's say, for example, let's say that n is 3, then 0, 0, 0, and j is 1. Let's say, for example, j is 1, n is 3. Then what you'll have is 0, 0, 0, 0, 0, 1, 0, 1, 0. Let me try to draw these in different places. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So 1, 2, 3, 4, 5, 6, 7, 8. And then now everybody gets paired with their flip. So if j is 1, that means this guy got paired with this guy, so they're a pair. 0, 1, 0 got paired with 1, 1, 0. That's a pair. That's a pair. And that's a pair. Right? So that's what I'm saying. Just take all these 2 to the n different x's and pair them up based on their flips. And what this observation is saying is, in each pair, so let's look at a pair. In each pair, either neither of them is bad, like neither of them makes us realize that AB is different from C. Oh, sorry. Neither is bad means both of them are good. Both of them are good, so both of them, no matter which one we pick, both of them makes us realize that AB is not equal to C. Or if one is bad, the other one has to be good. So if one of them makes us fail to realize it, then the other one will make us realize it. Which means this implies that the number of x such that ABX is equal to CX is at most a half of all of them. It's almost half of all the binary vectors. Which implies exactly what we want. Which implies that if you pick a random x, the probability that ABX is equal to CX is at most a half. Which is exactly what we wanted. So we're done. That's an analysis of Freival's algorithm. And I do want to point out that a natural thing that people might think is, why don't I just pick like a random, why don't I just pick like one random entry of C and just check that that random entry was computed correctly? Okay. How long does it take to check one entry of C? Well, Cij is just the ith row of A dotted with the jth column of B. That dot product takes linear time, n time. So just checking one entry of C would only take n time. But that doesn't work because, as I mentioned, who knows what kind of bug the cloud had, right? It might be the case that all n squared minus 1 entries of C are correct. There's just one entry that's incorrect, and who knows where that is. So it's very, if you just pick a random entry to check, it's very unlikely that you'll actually choose to pick that wrong random entry, right? So that doesn't, just sampling a random entry of C doesn't quite work. But Freival's does work, and it does give you quadratic time to get arbitrarily good confidence. Okay. So that's one Monte Carlo algorithm, and I think I have time to show you one more. And the second one is going to be for the problem which is global min-cut. And I'll describe that in a second. Let me erase all this stuff. Okay, so what is global min-cut? Today we'll just assume it's the following setup. We're given. So actually, before I say the problem statement, let me define a cut. A cut of a graph is a partition of its vertices into two non-empty sets. And we already talked about cuts when we talked about max flow, min cut. Remember? So there, we didn't talk about just general cuts. We talked about ST cuts. Right? There was a source S and there was a sink T. And an ST cut was exactly the same kind of definition, except we had these two non-empty sets. One was A and one was B. And we required that S was in A and T was in B. That's an ST cut, right? Where we require that these two special vertices are not in the same partition. More generally, a cut is just any partition into non-empty sets. So there aren't any two special vertices that we require be separated. And the size of a cut is the total weight of all edges. Let's say it's in a weighted graph crossing the cut. So we'll assume here that the graph is undirected. Also different, comparing with what we were talking about before with max flow min cut. We're focusing on directed graphs. So the global min cut problem is you're given as input a weighted undirected graph G, and you want to find a cut of minimum size. Now, even though this is undirected and we talked about the directed case before, you could always, one thing you could do is you could imagine that an undirected edge basically lets me flow in either direction. So I could turn it into, like if I had an undirected edge with weight 5, I could just make two edges, one in the forward direction and one in the backward direction, each with capacity 5, basically meaning I'm allowed to use this edge in either direction. So I could solve global min cut via n-1 calls to ST min cut. Right? Why is that? So I'm trying to find some partition into two non-empty sets. Vertex 1 is going to be in one of those sets. Okay? So let's just say that let's pretend that the source S is vertex 1. And in the optimal min cut, there's going to be, the partition that doesn't have 1 is non-empty. So it has something. So 1 is getting separated from some vertex. I just don't know which. So let me just call that vertex T. And again, I don't know what T should be. So I'll just loop over all possibilities for T. And then I'll pick the, and then for each one, I'll compute the ST min cut. And then I'll just return the min of those. So does that make sense? So what I'll say is, okay, so I know 1 has to get separated from someone in the optimal min cut. So what's the 1-2 min cut? What's the optimal 1-2 min cut? What's the optimal 1-3 min cut? What's the optimal 1-4 min cut? All the way up to what's the optimal 1n min cut? Where when I say AB min cut, I'm trying to separate A from B, right? Or ST min cut. So I can do n-1 calls to ST min cut, where S is 1 and T ranges over everything else. And then I'll just return the smallest of all those n-1 cuts. Today, what I'll show you is that there's actually an algorithm. And how do I find those ST min cuts? Again, I use like Ford-Fulkerson. I use some flow algorithm. Today, what I'll show you is that there's a totally different randomized Monte Carlo approach that doesn't use flows at all. I will show you randomized algorithm for the case where all edge weights are 1. It turns out that this can be generalized to work with arbitrary edge weights. I just will not talk about it today. And this is an algorithm called Karger's algorithm. named after the person who came up with it, David Karger. He came up with it in the 90s. And actually, Karger has multiple min-cut algorithms. So I'll specifically say Karger's contraction algorithm. And what is the algorithm? So I won't write the pseudocode. I'll just show you how to run the algorithm on an input. And then it'll be clear what the algorithm is. So I have an undirected graph, which I said all the weights are 1, so it's unweighted. Let's give these vertices names, 1, 2, 3, 4. There are 4 edges here. Karger's contraction algorithm is going to pick one of these 4 edges uniformly at random and, quote unquote, contract it. So let's say that first Karger chooses to contract this edge randomly. So I'm not sure that color is super visible. Let me do it with red. So maybe Karger chooses to contract this edge. Okay, so what does that mean? So this is contracting. So contract 2 with 3, the edge 2, 3. So what does that mean? It means we're going to basically merge these 2 vertices into a super vertex and just pretend that that super vertex is now one vertex. So now we have the vertex 1, which has an edge to this glued vertex. I'm going to call that glued vertex the vertex 2, 3. So 1 now has an edge to 2, 3. And 2, 3 actually has 2 edges to vertex 4, because 2 had an edge to 4, but so did 3. And we're going to keep both of them. So now it's not a simple graph anymore. It's what's called a multigraph, because we're allowed to have multi-edges. So here now we have 4, and we have 2 edges between 2, 3, and 4. And then, now there are 3 edges in this graph. We're going to pick one uniformly at random and contract that. So maybe we'll choose to contract this one. So we contracted the edge between 1 and the vertex 2, 3. 2, 3 is now a vertex. And now what we have is here a vertex which is called 1, 2, 3. And it has 2 edges to the vertex 4. And then we're done, right? Because now you can basically view each supervertex as a partition. So we have 2 supervertices, right? So we have a partition into 2 pieces, which is exactly a cut. So basically one side of the cut is this partition 1, 2, 3. The other side of the cut is the partition 4. How many edges are crossing the cut? There are these 2 edges that are crossing the cut. So this here has cut size 2. Which is wrong, right? This is not the min cut. The min cut is put 1 by itself and 2, 3, 4 on the other side. Then there's only 1 edge crossing. That would actually be the min cut. But this is a randomized algorithm. It chose to randomly contract some things, and it got the wrong answer. Okay? So claim. So basically, that's the algorithm, right? So the algorithm is we're going to do, given a graph with n vertices, this is an iterative thing. We're going to do n minus 2 random contractions, right? So every time you do a random contraction, you decrease the number of vertices by 1, because you always take 2 vertices and then put them together. So the number of vertices always decrease by 1. You started with n. You're trying to get down to 2. So you need to do n minus 2 contractions to get down to 2 super vertices, and that's your partition into 2 pieces. So that's the algorithm. You're going to in a for loop, n minus 2 times, you're going to pick a random edge, and you're going to contract it. And then when you're done, you have 2 sets. You have 2 super vertices. That's your cut. Set 1 and set 2, and then you measure the size by looking at how many edges here are actually crossing that cut. And the claim is that the probability that Karger, I'll just call it Karger, even though it's Karger, that's short for Karger's contraction algorithm. Karger outputs a min cut is at least 1 over n choose 2. Which sounds absolutely terrible, right? I mean, I usually want the probability that I succeed to be like 99%. Here I'm saying that the probability that I succeed is going to 0 as the graph gets bigger. The probability that I succeed is 1 over n squared, roughly. But that's not a disaster, because the fix is the run Karger, let's say capital R times, and return the smallest cut it ever finds. So what's the probability that the fixed Karger fails to output a min cut? Well, it had to fail every single one of those R times. So the probability that it fails once is 1 minus 1 over n choose 2. That's the probability that it failed in one iteration. And the probability that it fails R times in a row is at most that to the rth power. Okay? And this is at most e to the minus r over n choose 2. A handy fact, this follows from Taylor's theorem from calculus, or convexity. For all x, 1 plus x is at most e to the x. That includes x being negative. So here I'm applying that to x being negative 1 over n choose 2. So 1 plus negative 1 over n choose 2 is at most e to the minus 1 over n choose 2, and then raise that to the rth power. And this is at most p if I pick r to be n choose 2 times, let's say, ln of 1 over p, the ceiling of that. Okay. So I can actually get my confidence to be really high, my failure probability to be really low by just repeating it a lot of times, right? So it turns out that this algorithm, I won't show you why, but it turns out that this algorithm, if you're careful about the details, can be implemented in n squared time. You need to repeat it roughly n squared times log 1 over p, to have good confidence that you'll actually find the min cut. So this implies that the total time for the fixed Karger, the one that works with a good probability, is O of n to the 4th times log of 1 over p. So the dominant thing here is it's an n to the 4th time algorithm. Okay? So now let's prove the claim. This is the main thing that we haven't proven yet. So proof of claim. In fact, I'll prove something stronger. Fix a particular min cut S bar, where S bar means V minus S. I actually claim 2, stronger claim, is that the probability that Karger outputs that cut is at least 1 over n choose 2. Right? Not only do you output a min cut with probability, some min cut with probability 1 over n choose 2, fix any min cut you want. The graph might have many different min cuts. The probability that you output a particular one is at least 1 over n choose 2. And by the way, note that this is the best you could possibly hope. Note that this implies that your graph has at most n choose 2 min cuts. So note implies G has at most n choose 2 min cuts, which is the best you could possibly hope for, which is tight. And why is that tight? Just take a cycle. Just take a cycle on n vertices. Right? What's the min cut value in a cycle? Basically, just like cut two edges. So your partition is going to be basically this arc and this arc. And the size of the cut is 2. How many ways are there to do this? Basically, choose any two edges to cut. Each one of those will give you a min cut. It'll give you a cut of size 2. There are n choose 2 ways to do this. Right? So the cycle in particular has exactly n choose 2 min cuts. So you're not going to be able to improve this 1 over n choose 2 for this claim. So let's prove claim 2 now. Okay. So let's look at this algorithm. So there's a particular min cut. So we have a particular min cut. In this case, for example, S is just the set that contains 1, and S bar is then everything else, 2, 3, 4. What I don't want to happen is I don't want to ever contract someone in S with someone in S bar. Right? I don't ever want to contract along an edge that actually goes across the cut. And that's exactly what happened right here. Right? I randomly contracted an edge that actually was in the min cut that I cared about. And then therefore I didn't actually output the min cut I wanted. Right? I didn't actually output the cut I wanted. So the probability that Karger outputs SS bar is exactly the probability that for all n minus 2 iterations, I never contract an edge which actually crosses that cut. So this means the set of edges that cross the cut. I never want to contract any edge that crosses that cut. So the probability that I never contract any edge E which crosses the cut means basically the probability that for all I going from 1 to n minus 2, I don't contract an edge crossing the cut in the ith iteration. And that's equal to the product, I goes from 1 to n minus 2, of the probability that I don't contract an edge E crossing the cut, given that I haven't so far. In the iteration so far. Okay. Now, notation, let's just say that the min cut value is k. I'm just defining k to be, it's whatever, k is whatever the min cut size is. So what's the probability, don't contract in iteration I, given that I haven't contracted one so far? What's the probability that I don't contract an edge crossing the cut in iteration I? Well, the probability that this is equal to now the product, I goes from 1 to n minus 2, of, so the cut is still there. Right? I haven't contracted anything crossing the cut yet. What's the probability in this iteration I continue to avoid that cut? Well, what's the probability that I do contract something that crosses the cut? Well, there are exactly k ways to do it. There are k edges that cross the cut. So the probability that I contract something that crosses the cut is k over the number of edges in this iteration. Mi is the number of edges that are still there in iteration I. And initially, in the first iteration, m1 is m. But notice in later steps, there might be fewer edges. Like here, there's 4 edges. Here, there are only 3 edges. Here, there are 2 edges. So m is constantly going down. So this is the probability that I do contract. So the probability that I don't contract is 1 minus this. Okay? Now, what can I say about mi? How many edges are there in iteration I? Well, note that for any vertex, there's always the cut which separates that vertex from the rest of the graph. And its size is basically the degree of that vertex. So since I know that the min-cut value is k, even in the later iterations I know that the min-cut value is k, because I haven't contracted the min-cut itself yet. So the min-cut in particular, the cut SS bar is still there, which is a cut of size k. And contracting will never shrink the size of the min-cut. What this says basically is like basically for all vertices v, the degree of v has to be at least k. Right? Otherwise, there would be some singleton partition where some vertex would go by itself with everything else. That would give me a cut smaller than the min-cut. But there is nothing smaller than the min-cut. So all the degrees have to be at least k. But now notice that mi is basically the sum over all vertices of the degree of that vertex divided by a half. Right? If you sum up all degrees in the graph, you get exactly twice the number of edges. Okay? So this implies, and since all these dv's are at least k, this implies that mi is at least 1/2 times k times ni. Okay. And what's ni? Ni is just n minus I plus 1. Right? In iteration 1, there are n vertices. In iteration 2, there are n minus 1 vertices. In iteration 3, there are n minus 2 vertices. The number of vertices always goes down by 1. So that implies that this thing is at least, so m is at least something. So k over m is at most something. So 1 minus k over m is at least something. So this is at least the probability I goes from 1 to n minus 2 of 1 minus k over 2 times n minus I plus 1. The k's cancel. So this is the same thing as the product I goes from 1 to n minus 2 of 1 minus 2 over n minus I plus 1. And now we're basically almost done. What is this thing? This is equal to 1 minus 2 over n times 1 minus 2 over n minus 1 times 1 minus 2 over n minus 2 times dot 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 times. So the last case, it's when I is equal to n minus 2, n minus 2, which is 2, plus 1 is 3, 2/3, 1 minus 2/3 is 1/3. So times 1 minus 2/3, which is 1/3. And this is the same thing as n minus 2 over n times n minus 3 over n minus 1 times n minus 4 over n minus 2 times n minus 5 over n minus 3 times dot dot dot. And then here I have, yeah, that's right. And here I have 1/3, and here I have 2/4, 3/5, etc. And lo and behold, n minus 2 cancels that n minus 2, n minus 3 cancels that n minus 3, n minus 4 will cancel this thing here, etc. This 3 will cancel with this 3. There'll be a 4 here, which will cancel with this 4. This 5 will cancel with this 5, etc. At the end of the day, what this will equal is 1 over n times 1 over n minus 1 times a bunch of 1s, because everything canceled in the middle, times 2 times 1, which is exactly 2 times 1 over n times n minus 1, which is exactly 1 over n choose 2. So that's it. Okay. So we've analyzed Carter's algorithm. Okay. So that's all I wanted to talk to you about today regarding randomized algorithms. We got to see one Las Vegas algorithm, namely quicksort, and we analyzed 2 Monte Carlo algorithms as well, Freival's algorithm and Carter's algorithm. So thank you.